In the previous online lectures, we learned how to do reactions on the alpha carbons. We know how to do alpha halogenation, and we know how to do alpha alkylation. So go ahead and try. How do you make this ketone using what you've learned from acetophenone? Here's the acetophenone, and here's the ketone you want to make. Well, if I look at this, you can see that the difference between these is just these 1, 2, 3, 4, 5 carbons. So this could be a simple alkylation. If I treat this with LDA, I will get complete formation of the enolate here, and then treatment of a primary alkyl halide will give us an SN2 on that primary carbon, and we end up making this ketone. Beta carbonyl esters. What's a beta carbonyl ester? That is where you have an ester with this is the alpha carbon, that's a beta carbon. Here is here's an ester. This is the ester. It's not been deprotonated. Here is the alpha carbon. There is the beta carbon. When you have two together, they're more acidic than just one, and so we can use something like sodium ethoxide to form 100% of the enolate. You get 100% deprotonation. What's special about beta carbonyl esters is what we can do after we alkylate. So let's just look at this example down here. We can take this beta carbonyl ester, treat it with, take the enolate, treat it with an alkyl halide, notice it's primary, and we end up getting substitution on the alpha carbon. If I treat with acid and heat, it will change the ester to the carboxylic acid. Once I have the dicarboxylic acid here, this acid that is alpha, basically you have an acid group alpha to the other carbonyl, you end up having decarboxylation, and so this whole part gets removed. This is what happens. Here is a carbonyl, and beta to it is this carboxylic acid functional group. You have a carboxylate on the alpha carbon. You have a carboxylic acid functional group on the beta carbon, however you want to look at it. When you heat with acid, what happens is you get this arrangement in space, and you can have a paracyclic reaction. And notice carbon dioxide is eliminated, and we end up forming the enol. The enol then tautomerizes back to the carbonyl. We have two name reactions that use this principle. There's the malonic ester synthesis. This is called the malonic acid is basically 1,3 propanoic acid, propane dioic acid. Malonic ester synthesis is we take the ester of it and we end up alkylating and then decarboxylating. The acetoacetic ester synthesis this is called acetoacetic acid ester. If you look at this as being acetic acid, this is an aceto group that's on it, and that's where it gets its name. This can be used in the synthesis by alkylating and then decarboxylating. And look and see what the net effect is. Up here, we can take an alkyl group, remove the halide, and basically add an acetic acid group onto that primary carbon. Here we can this looks like acetone that we've just tacked onto a carbon. So let's look at some examples of this. Okay, here is our malonic acid. Okay, it's basically propane dioic acid ester, diethyl propane dioate, and right here is our alkyl halide. We're going to treat with sodium hydroxide, and that deprotonates. And what happens? We do SN2 on this, and we end up getting this adduct. If I treat with acid and heat, that whole thing gets cleaved off. This other ester is also brought down to the carboxylic acid functional group, but you cleave off one of those esters. And look what the net effect is. Here are those 4 carbons. Here are those 4 carbons. And then here is basically what looks like acetic acid being tacked onto that alkyl group. So what is that? That's this carbon and one of these carbons in an ester group that's been taken down to an acid. So you can kind of look at these 2 hydrogens, at least one of them being right here. If you want to, you could do it again. You could alkylate twice. Deprotonate, sodium methoxide, alkylate again. Notice what we get. We get both alkyl groups on there. Now when we did decarboxylate, you can see one alkyl group from up here. Here's the other alkyl group. Here's another example. Malonic acid ester enolate. Here I'm going to do an SN2 on this end of the carbon. We're going to do it again with another sodium methoxide and do SN2 on that end of the carbon. Now you see both ends have been attached to that carbon. We heat, and that's going to cleave the ester into an acid functional group, and then we're going to lose the other acid as carbon dioxide. And look what we get. These 2 carbons come from where? Here and here. These 5 carbons come from where? This carbon and those 4. So this carbon used to be right here. Those 4 carbons used to be where? Right here. So how can you make this ketone from this ester? Well, let's look and see where the carbons come from. You can see we've got the cyclohexanone here, and there's cyclohexanone here. What are the extra carbons that we see here? Here, 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 all these. That's basically benzyl. And where is this functional group? We'll notice that it's it's a beta carboxylic ester, which can be changed to a beta carboxylic acid and then decarboxylated. So what is the intermediate between these 2? It's got to be this. You see that I can deprotonate this and alkylate. Now, how can I go from here to here? Well, that's just treat with acid and decarboxylate. So what reagents do I need to alkylate this dicarbonyl compound? Sodium methoxide is a strong enough base, and then I can use benzyl bromide. Once I get this intermediate, then all I have to do is treat with acid and heat, and it will decarboxylate this. Go ahead and try this. Try to make, this is methyl cyclohexyl ketone from 1,5-dibromopentane. Well, 5 carbons. Where are there 5 carbons? It would have to be in here. 1, 2, 3, 4, 5. If I look at this, this looks like acetone if I cut these bonds. That makes you think of the acetoacetic ester synthesis. So what can I use as my alkyl groups? 1, 2, 3, 4, 5, the 1,5-dibromopentane. And what do I use as my starting material with the carbonyl? I'm going to use this. This is, you see, remember you can decarboxylate this off, and this is going to end up being here. This carbon will end up being that carbon. I can treat with ethoxide, that's a strong enough base, and then treat with 1,5-dibromopentane, and I end up getting this. Now all I have to do is treat with base again, and what's going to happen? Deprotonation occurs, SN2 on this end of the alkyl halide, and we end up getting this intermediate. I can decarboxylate that by treating with acid and heating. That's going to change that to an acid group, and then it's going to leave as carbon dioxide, and I end up getting the product that I want. Go ahead and make 3-phenyl propanoic acid from benzyl bromide. Well, here's benzyl bromide, and here's 3-phenylpropanoic acid. How can I go from here to there? Again, notice these are the carbons that are in the benzyl bromide. These are the carbons that have to come from some kind of carbonyl compound. Well, if I make this, I can add what's equivalent to acetic acid with the acetic acid ester. So this is, wrong. This is acetic acid, and I can add the equivalent of acetic acid with the malonic ester. And so here's malonic ester, and what we're going to do is deprotonate there with ethoxide. If I treat with this alkyl halide, then I get, and then decarboxylate, I end up getting this product. So now, which one of the following would undergo a haloform reaction? If you remember, in the haloform reaction, we treat with sodium hydroxide and bromine or chlorine or iodine, and it will take a methyl ketone and change it to a carboxylic acid. So I actually have to look for a methyl ketone here. This would not work. This is not an aldehyde or ketone, so it would not work. This would not work because it's not an aldehyde, or a ketone. Acetophenone is a methyl ketone, and acetone is a methyl ketone. So both of these would end up undergoing the haloform reaction. Treating acetone with the under haloform reaction conditions would give you acetic acid, and acetophenone would end up giving you benzoic acid. What is the predominant enol of this dicarbonyl compound? Well, you're not going to form a dienol. So what enol will form? If I want to throw these out because you won't form a dienol. If I look at this one and this one, it's between those. Which way would the enol be more stable? Well, here the ene is conjugated to the carbonyl, so it's more stable and it would form. What will occur to this optically active compound in acid? It would form an acetal? I don't think so. First of all, it's not an aldehyde, and aldehydes form acetals. It would form a diol. Well, what you might have chosen that if you were thinking about a geminal diol, which we basically would call a ketone hydrate. Can it do that? Well, yeah. It would become an alcohol? No, acid is not a reducing agent. It will lose its optical activity? Well, yes, because what happens with a ketone in acid is you form the enol. The enol would become planar right here, and then you could have tautomerization, putting the proton on either side. So this is the correct answer. The diol, yes, you would form a geminal diol, a ketone hydrate, but that would be a minor reaction. The real reaction that would be significant would be enolization that would cause optical activity to be lost. What is the product of bromine and acetic acid with this ketone? Well, which way would the enol form is what you have to think. The more stable enol would be more substituted. You're not going to lose a methyl group, so you can throw that out. You're not going to form that because the enol would be more stable this direction. It's not going to give you have you lose an alkyl group. This is not the haloform reaction. And again, that's not the haloform reaction. This is the only one that makes sense.